two discrete springs, and also we have one discrete damper. Okay, so in the solution, usually the diffraction function is given. Okay, the phi function is given, and you have to look into the question. For example, where is the location for the generalized coordinate? Okay, in the tutorial, in the assignment or midterm test or final examination, I should provide you the generalized coordinate. But if for a real problem, you can assume any location as a generalized coordinate. But in examination or in midterm test, I have to provide a specific location as a generalized coordinate. Otherwise, different students will get different solution about the response. Okay, so here I provide you the middle span as a generalized coordinate. So the diffraction at the middle span is a generalized coordinate. That means the function phi should be equal to 1 at this point. If it is not equal to 1, you have to normalize it. Okay, and in this structure, because structure is symmetric, response also symmetric. So when you do the integration, you just need to integrate half of the structure. Okay, but it does not mean you consider half of the structure. Please understand the difference. I will show you. Okay, you still consider the entire structure. Okay, for example, here you should integrate from this point to this point, but because it is symmetric, so the integration from this point to this point is equal to 2 times the integration from this point to this point. Okay, but we still consider the whole structure, not just half of structure. Okay, so please understand the difference. Because if you consider half of structure, so M2 will be separated into 2 mass. Okay, each one with a mass equal to M2 over 2. It's not so good. It's not a good idea. I do not recommend you to separate the structure into 2 parts. You just need to consider, when you do the integration, you just need to do the integration for half of the total range, because response and the structure are both symmetric. That's all. Okay, so this is a full step. Okay, when we apply the equivalent single degree freedom system, we always use this formula. Okay, and then the phi function. Okay, now because the generalized coordinate at the middle span is equal to x is equal to L over 2. So phi L over 2 must be equal to 1. It is not equal to 1, you have to normalize it. Okay, and also you have to calculate the diffraction function and the square of the diffraction function. But in the midterm test or final examination, I will assume the phi function very simple. Okay, it's just a linear or power function, not complicated function like this one. Okay, so don't worry about the calculation about the second derivative and the square of the function, something like this. Okay, so and then we can calculate the kinetic energy. Okay, so this is a formula to calculate the kinetic energy for the original system. We have both distributed mass as well as concentrated mass. Okay, and this is the kinetic energy for the equivalent single degree freedom system. If you want me to provide you marks, please try to write down your solution as detailed as possible. For example, you can write down equation this like. Okay, so if you can write down an expansion like this, even you get the final solution about T0 is not correct, I can still provide you marks. Okay, if you do not provide a standard formula like this, you just provide me T0. If the T0 is not correct, I couldn't provide the marks. Okay, so please always try to do something, to make me can provide you marks. Okay, it's very important. Okay, if you did nothing, I cannot provide you marks. Okay, so please always try to do something. And this is original the kinetic energy for the original system. This is standard formula. You just need to write down standard formula again. And this is a standard formula for the equivalent system. Okay, and by equating T0 with TE, you can obtain the equivalent mass. So this is an equivalent mass, okay? You can obtain the expansion like this, and then finally substitute the detailed expansion about the phi function to get the solution. Because if you can write down the expansion like this, I will almost provide you full marks even you get final solution about the generalized mass incorrect. Okay, if you can write down the expansion like this, I will provide almost full marks to you. Okay, and then we can obtain the potential energy. For our problem, we don't have distributed springs, so you just need to calculate the shear energy due to the bending of the beam, as well as the potential energy due to the two springs. We have two springs here. Okay, we have two springs here, so we can so this is an expansion for the potential energy, and this is an equivalent system. So by equating V0 with VE, we can obtain the generalized stiffness. So this is the generalized stiffness. Okay, this is the results, and also for the virtual work done by the damping force for the original system, we have a standard formula, and in our problem we don't have distributed stiffness, distributed damping. So the first term is equal to 0. So we only have the second term. Sorry, we don't have this term is equal to 0. So this is a general expansion. Okay, this is a general expansion. We assume distributed damping, but final solution this term is equal to 0. Okay, because we don't have a distributed damping. So actually you don't need to include first term in the expansion. You can move. Okay, you can remove this term from the expansion. Okay, and this is a generalized expansion for the equivalent system. And then by equating W0 with WE, you can obtain the generalized damping. And this is generalized damping. And in this special case, you find the generalized damping is just equal to the original damping. I will tell you why. Okay. And also, how about the force? For this problem, we have both distributed force and concentrated force. So you have to consider two terms. Okay. And for the distributed force, you have to complete the integration. Okay, but for this problem, I want to mention, because some students make mistake in the calculation about the integration. Because the force, the distributed force, is applied just for one specific range, not covering the whole length of the beam. So the integration should be take from here to here. Okay, so from at this point, x is equal to L over 3. At this point, L over 6 plus L over 6 is equal to L over 3. So from this point to this point. And because this part is same as this part, so the integration from here to here actually is equal to integration from x equal to L over 3, okay, to x equal to L over 2, from here to here. And then the final, and then add a coefficient 2 before the integration. So here I provide, okay, so for the equivalent force, here is L over 3, okay, to L over 2, okay, over L over 3 to L over 2, okay. Again, here's a L over 2 to 2L over 3. So this is the first part. This is the first part from here to here, okay, from here to here. Because we have a different expansion. This is a linear expansion, and this is a different linear expansion, right? So from here to here first, and then from here to here. Okay, actually, you don't need to calculate two times. Actually, the integration for the first part is same as integration for the second part. So you just need to add a coefficient 2 here, and then eliminate the second integral. Again, this term is same as this term. So this term is same as this, so you can eliminate this term and put the coefficient 2 here. So we can obtain the generalized coordinate force. So we have obtained the generalized mass, generalized damping, generalized stiffness, and generalized force. So we can write down the governing equation. So this is the governing equation. And from this equation, you can obtain the undamped natural frequency. and also the frequency inverse, and also you can obtain the damping ratio. Okay, this is a definition provided, okay, for single degree freedom at the beginning of the lecture. Okay, so you just need to use the previous, the formula given in the previous lecture. Okay, so this is the first example, and then we go to the second example. In the second example, we have a distributed mass and concentrated mass. The force is linearly distributed, okay, and we have two dampers. And in this case, we use a very simple shift function. Okay, so this is shift function, and I hope you can use in the final examination or midterm test. We always have a shift function, simple shift function like this. Okay, and in this question, we take the response at this free end. Okay, we take the response at the free end as a generalized response, as a generalized coordinate. Sorry, as a generalized coordinate. So assume that the diffraction shift in this function, and consider the transverse response at the top as a generalized coordinate, and then we can obtain the equivalent or generalized damping force, damping stiffness, mass, and force. Okay, so this is a solution. Okay, this is a solution. I hope you can check phi function. Okay, phi function should be equal to 1 when x is equal to 0. Okay, if it is not equal to 1, please normalize it. Okay, I mentioned this several times, but in midterm tests in the previous year, some students still make mistake. Okay, and this is a this is expansion to calculate the kinetic energy for the original system. We have a distributed mass and a concentrated mass. Okay, and this is standard formula. And then, based on the equivalence of these two expansions, we can obtain the generalized mass. Okay, okay, this is a generalized mass, and this is the potential energy. We don't have any springs, so we just need to calculate the strain energy due to the bending. Okay, bending, and this is a standard formula for the equivalent system. So based on the equivalence of these two expansions, we can obtain the equivalent stiffness. Okay, and for the damping force, we have two dampers. So you have to calculate the motor work done by two damping forces. Okay, two damping forces at different locations. Okay, again, it involves square of the phi function. Okay, I mentioned many times. Okay, it involves square of the phi function, and this is the equivalent system. And from the equivalence of two expansions, we can obtain the generalized damping. Okay, and for the force, please understand force is a linear distributed, so it is a function about x, linear function about x. Okay, so you can also we can obtain the standard formula for the equivalent system, and then based on the equivalence of two expansions, we can obtain the generalized force. Okay, and this is the final equation, and this is a damping coefficient. Okay, damping coefficient. So today I just talk about the equivalent single degree freedom system mesh. Tomorrow, next week, I will talk about the earthquake response analysis. Okay, I want to review these two examples. Okay, you can see. Okay, I can give you some hint. Okay, for example, for the first example, okay, the equivalent damping is just equal to the original damping. Why? Because we take this point as a generalized coordinate, and the damper is just attached at the generalized coordinate location. When damping stiffness or mass is just at the location of the generalized coordinate, its contribution to the equivalent damping, equivalent stiffness, or equivalent mass must be just equal to the original damping, original stiffness, and original mass. Okay, so in this case, we take this point as a generalized coordinate. So the equivalent damping from this damper is just equal to C. So the contribution is just equal to C. So this is a good idea. You can check your solution. Okay, and similarly, because M2 M2 is at the generalized mass, generalized coordinate location. So the contribution to the generalized mass from M2 must be just M2. But the contribution from 2M1 will be different from M1. Okay, because M1 is not located at this generalized coordinate location. So you can check. Okay, so we can go to, for example, you can see M2, okay, is just equal to M2. But M1 is not equal to 2M1. Okay, we have 2 M1, but it is not equal to M1 because the 2M1 are not located at the generalized coordinate. Okay, so and how about the situation from the second example? From the second example, okay, because this mass is just located at a generalized coordinate location. So this mass is for the concentrated mass, its contribution to the generalized mass is just equal to the original mass. But for the distributed mass, it's definitely different from the original distributed mass because distributed mass is located at different location. So it is impossible at the location of the generalized coordinate, right? So this is the result, okay? And if you change, for example, if you change the generalized coordinate, okay, from this location to this location, if you take response at this point, okay, as a generalized coordinate, and then the contribution of this spring to the generalized stiffness must be equal to K. Okay, so please understand this point. So that means you don't need to calculate. Okay, you don't need to calculate if the mass stiffness or damper is just located at the generalized coordinate location. Its contribution is just equal to the original value. Okay, original value. So this is important. Okay, so I have shown you the solution. The lecture on the equivalent single degree freedom method. You just need to use a standard formula, okay, given in the summary list. Okay, just need to use the standard formulas given in the summary list to get the solution step by step. Okay, so now I show you the solution to the questions in tutorial 6. Okay, tutorial 6.